Okay, so welcome back once again to our channel, and this time we continue discussion about the adder circuits. In the previous model, we talked about half adder and full adders, and now this time we talk about n-bit binary adder. So as you can see on your screen, this is a schematic of a half adder circuit, and it has got two inputs A and B. It has got two outputs sum and carry. So since there are two inputs in binary, 2 to the power 2, that is equal to 4 input possible combinations are there, starting from 0 0 0 1 1 0 and 1 1. So for the combination of 1 1, you have sum is equal to 0 and carry is equal to 1. So you got the carry generated when you have both bits A and B to be equal to 1. And this circuit is called as half adder because of this addition of 1 1, you got the carry is equal to 1. This carry generated is not being taken care of by the half adder. That's why it is called as half adder. Now, to solve this problem, we have another circuit called as full adder. Here, instead of two, you have three inputs, A, B, and C in. So, how to understand this? This C in, if it is equal to 1, that is going inside the full adder to be added with A and B. So now because of the three inputs A, B, C in the binary, you have 2 to the power 3, 8 possible input combinations. And why we are calling it as a full adder? Because of the addition of A and B, if that carry is generated to be equal to 1, this carry goes in to be added with A and B, finally giving you a full addition of the bits, and two outputs are sum and C out. That's why we call it as a full adder. So we've seen the inside circuit of half adder and full adder in the previous module. Now a small question here. Your sum is generated and carry is generated. If the carry generated here is again equal to 1, what we do with the carry? It's up to us, so we can ignore or neglect it. But we are calling it full adder because if the carry is generated from the previous addition of A and B, and C is equal to therefore equal to 1, that goes and taken into account by the full adder. That's why we call it as a full adder. So now let us talk about n-bit binary adder. So to make the n-bit binary adder, what you do is you take 1-bit full adder unit. So it has got three inputs, A naught, B naught, and C naught, and it has got two outputs as sum and carry, that is S naught and C1, that is carry 1 here. So A naught and B naught and C naught, each of them are single bits. They can have value of logic 0 or logic 1. Then you take another 1-bit full adder. It has got inputs A1, B1, and C1, which is basically a carry output of the previous full adder stage. And it has got two outputs, that is C2 and S1. Then you keep on cascading such full adder. This is the third stage, which has input A2, B2, and the third input is C2, which is the carry output of the second full 1-bit full adder. And it has got two outputs, C3 and S2. You keep on doing that up to the 1-bit full adder of the stage called as with the inputs an minus 1, bn minus 1, and the carry input of this would be cn minus 1, and the two outputs of it is cn and sn minus 1. So that is how you build your complete circuit here of n-bit binary adder. So you can see that this is also called as a series adder circuit. Why? Because you are adding the initial 3 bits, assuming C0 is equal to 0, you have two outputs available, S0 and C1. And then C1 propagates to the second stage, giving the sum and the carry output of this stage. So unless the C1 comes here and gets processed inside this circuit, you have to wait for the sum output right over here. Similarly, then the outputs are presented here. This carry ripples to the next stage. So you see that your carry gets rippled or propagate from one stage to the another, and that's why it is a series addition. So it is n-bit series adder. It is also called as n-bit full adder, or it is also called as n-bit carry ripple adder, because carry ripples through the stages of this full adder circuit. So this is the serial adder, as we've said this before. Now with the n-bit adder, what about giving an example? Let's say we want to implement a 4-bit binary adder, which is also called as 4-bit carry ripple adder. So as the name suggests, we need 4-bit binary adder. It means we'll take 4 1-bit full adders. Each of these full adders, you can see that they have the inputs called as A0, B0, C0, and the sum and the carry. Again, A1, B1, C1, sum and the carry. Here, A2, B2, C2, sum and the carry. And then A3, B3, C3, sum and the carry. So this is how the full 4-adder circuit will be implemented. It is also possible that you have 8-bit binary adder, 16-bit binary adder, 32-bit carry ripple or ripple carry adder, 64-bit, 128-bit, so on and so forth. So in the modern ALUs, arithmetic logic units, where the adders are integral part of the ALUs, and then ALUs are part of microprocessors or DSPs or microcontrollers, the bit width of the adder circuit is 64-bit minimum, 128-bit, 256 bits, and so on and so forth. So that is the function of the and the concept of the full adder. Now, as you can see that inside the full adder, you have logic implementation, and that logic gates implements your full adder circuit, but the carry is propagating from stage 1 to stage 2 and stage 2 to stage 3 and so on up to the 4th stage here. So that introduced a delay, because as I said here, the sum is available at the outputs of the full adder one by one only when the carry gets inside the full adder, and there is this logic gates inside the logic gates. You have transistors, you have with the transistors you have capacitances and the resistance that introduces the propagation delay, and therefore the series addition is a slow process. These kind of adder circuits are slow circuits because of the carry propagation delay, and that's why we are also calling it as a ripple carry or carry ripple adder. So for the smaller bits, for example 4-bit or 8-bit, this is okay. You can do such addition by implementing the full adder circuits and cascading them together in the series. But for large bit widths such as 64, 128, 256, and so on, this is a tremendous task and not advisable. So this is an example of how the 4-bit binary adder will work. So example, you have a number A, number B, each 4 bits. This is the bit width of number A, 0, 1, 1, 1. In decimal, this is number 7. This is the bit width of number B, 1001, which is decimal 9. So in decimal, the addition of 9 and 7 gives us 16. So in the binary, we'll do this addition now. So C naught is equal to 0, which is, if we focus here, C naught is 0, and we have to add A naught and B naught. So in number A, this is A naught, LSB, least significant bit. In number B, this is LSB, that is least significant bit, that is B naught. So this is A naught and B naught. This is A1 and B1. This is A2, B2, and this is A3 and B3. So that's what precisely we can see in the schematic. So this is the MSB of number A, most significant bit. This is the MSB of number B, most significant bit. So we start from C naught is equal to 0. Obviously, we don't have any carry coming in to the circuit inside. A naught and B naught both are 1, which are A naught and B naught here. They go inside, C naught comes in, and the full adder circuit inside is basically two half adders, for example, cascaded. Half adder is nothing but XOR and AND gate. So we need two such gates and then one OR gate to finally make one full bit adder. We have seen this circuit in the previous model, so refer to that. So 1 plus 1 sum is 0, carry got generated, that is C1 is equal to 1. So carry got generated here. C1 is 1, A1 is 1, B1 is 0. So 1 plus 1 again sum is 0, carry got generated at C2. So C2 gets propagated to the next stage. C2 is 1, A2 is 1, but B2 is 0. Again 1 plus 1 sum is 0, carry got generated at C3. C3 is put up here. A3 is 0, but B3 is 1. Again, 1 plus 1 is 0. C4 got generated. C4 is 1, which is put up here. But you don't have A and B numbers here. So C4, you can neglect it or ignore it. Finally, in binary, the sum of number A and B, 4 bits each, would be 0, 0, 0, 0 here, but the MSB is 1. You put up 1 here. So final number is 5 bit 10000, which is in decimal is equal to 16. So we've seen that 9 plus 7 is 16. So this is how 4-bit addition has been done serially. So you can see that carry is getting rippled or propagated from previous stage to the next stage. That is why it is called as ripple carry adder. So this is a slow process. This is the schematic representation how the 4-bit binary adder will look like. There is an IC available in the market with the name 74LS83. You can Google this number and you can get the datasheet of this IC. So this is the bit width of number A3, A2, A1, A0. This is the bit width of number B3, B2, B1, B0. This is C in, that is the carry goes in. This is the C out, carry comes out. So C in here can be 0 because we are just starting the addition. And C out would be whatever generated. If the carry got generated here, you can neglect it or ignore it. Sum is also a bit width of 4. S3 being MSB, S0 being LSB. So this is how your 4-bit binary adder works. Hope you found this model useful. If you did so, share it with others for wider reach and stay tuned for more engaging content like this. Till then, wish you happy learning.